Hey guys, so I'm going to be talking all about time today, and I would really try to have the Stellarium web page open to go through because we'll do some work with that and kind of see how some of this time stuff works that you can see right on Stellarium. So, one of the first things we want to talk about, obviously, is the length of the day. And most everybody, I'm sure, has a basic awareness. We measure this by the sun's motion. But I want you to stop and think, what are we actually measuring to come up with a 24-hour day? And if you're like a lot of kids, you're probably thinking, I'm going to measure from sunrise to sunset. But remember, from what we've already talked about, the placement and the timing of the sunrise and sunset is going to change throughout the year. So, wintertime, we have a very brief period from sunrise to sunset versus summertime, we have a very long time period. So, sunrise to sunset is going to be a very bad way to try to measure out a day. But remember that we also know that halfway between sunrise and sunset, that's when the sun should be at its highest peak. Doesn't matter where you are, unless you're at the poles and there you never see anything rise or set. Anywhere else, you should see the sun rise and eventually set. So, halfway in between is going to be when the sun or any celestial object is at its highest peak. And so, we call this the meridian, just like meridians are lines of longitude. It's really the same exact thing. It's an imaginary line that points north south. We just now notice extend it out into space. Instead of just having it a line on the ground, we can extend it out into the celestial sphere. And so again, everything's going to rise roughly in the east, reach its highest peak at your meridian, and then sink back down and set in the west. So no matter where you're at, you could look to the south, you could watch the sunrise, you could watch the moonrise. It's going to come up, it's going to hit your meridian, and then it's going to sink back down. And that meridian then is defining the line between north and south. So that is what noon is supposed to mean. You might hear it called in astronomy local noon or solar noon or apparent noon or any combination of those. But that is when the sun is on the meridian at its highest altitude. The sun rises up, hits the meridian, and starts to sink back down. So I want you to get Stellarium out. So up here, I would go and I would turn on your meridian, probably turn on the ecliptic too, but definitely get that meridian on. Again, here's where the app is, and then you can hit that button right there to make all that stuff go away so you can get a much better view. Notice there's my nice green meridian. The red line's my ecliptic. So make sure you're at north central. Make sure you've turned time to today. And I would turn on your constellations and your equatorial grid, and then look to the south. And what I want you to do is to try to adjust the time until you get the sun right on the meridian and see what time that happens. You might want to turn off the atmosphere to make that easier. You might want to click on the sun to bring up this information so that you can see the highest altitude. You can see when its azimuth is exactly 180 degrees. That's when it's going to be on your meridian. So hopefully you found something stupid like it's nearly 1 p.m. until the sun is on the meridian. And we're not even on daylight savings time, so our local noon is definitely very different from noon on the clock that we have for Eastern Standard Time. But this basic concept of sunrise hits the meridian, sunset, this is actually where we get our AM and PM. AM means ante-meridium, PM post-meridium, essentially before the meridian, your local meridian, and after the local meridian. So AM to PM. And so at midnight, that's where the transition, because everything here is before the meridian. So that might be a way to help you remember that 12 p.m. is supposed to be noontime. So then we are going to say specifically that a solar day measures from noon to noon. That way we can make sure we're getting the best measurement possible. And of course, you all know one solar day equals how much time? Not 24 hours. In fact, that only happens as an average. We call that the mean solar day. So we're going to find that day to day, we're not exactly 24 hours. Only on average throughout the year do we actually hit this 24 hours. So a mean solar day, we just declare it to be exactly 24 hours, which if we say, well, how many minutes, how many seconds, and all of that, there's exactly 86,400 seconds in a mean solar day. So what's going on here? Well, an apparent solar day is when we just measure from solar noon to solar noon. And what you're going to find, if you did that, you would notice between 30 seconds to 20 seconds off from that mean. And this is happening because remember, the Earth is also going around the sun. And I've mentioned before, our speed is going to actually change as we go around the sun because we're not going in a perfect circle. As we get closer, we speed up. As we get further away, we slow down. This funny thing is called the equation of time, and this is trying to show the difference between clock time and solar time, showing, hey, we're getting really far off, we're getting below, we're getting behind where we should be, hey, we're getting ahead of where we should be, hey, we're back to where we should be, behind again, back to where we should be. And so this is going to happen because we have two fundamentally different motions, our rotation and our revolution. They are two different motions here. So this thing you might have seen on these little fancy globes, this little fancy figure eight, that's not just trying to be fancy for no reason. That's called an analemma, and that's showing you the position of the sun at the same time over the course of a year. So this picture over here, this dude literally went to the same place, same time. He spread them out a few weeks apart and basically took a picture of where the sun was. Same exact setup. Came back a couple weeks later, another picture, and here you can see the movement of the sun. So this motion, this up and down motion, is primarily through the seasons, right? Here's going to be what we call the summer solstice. Here's our winter solstice. And so there's that change throughout the course of the year. But this back and forth motion, that's because an apparent solar day is not 24 hours. Only a mean solar day is 24 hours. And so that's why we get this just slow kind of figure eight throughout the course of a year. Here you can kind of see that happen. Again, a view during sunrise in Washington, D.C. If we did not change the speed of our orbit, we would just go back and forth through the seasons. So you can actually do this on Stellarium. So go back to Stellarium. In a second, I'm going to have you pause it. Put the sun right on the meridian. It's up to you what might be easiest, whether you have the constellations and atmosphere on or off. Here I've turned them off. So what I want you to do, once you have the sun sitting on the meridian, then start clicking on a day and just really let it go. And as you're coming back, now you might be going, well, hey, what about that big jump? I kind of saw the figure eight, but there was a couple times where I had that big jump. I want you to stop for a second, do it again, and see when that happened. So that big jump, that's all because of the daylight savings time. The slow, steady figure eight-ish appearance, that's because of our changing speed revolving around the sun. The big jumps, just because of silly daylight savings time. So you might be wondering, does this mean that the rotational speed of planet Earth, is that changing or not? We should be able to feel that, and the good news is, in fact, it's not changing. That part is really consistent. So we're going to have a different way of measuring the true rotational speed of planet Earth, and that's the sidereal day. The sidereal day is exactly 23 hours, 56 minutes, and 4 seconds. Every day, all year long, And that's the way it is. So you're going to see the term sidereal a lot. That means always measured by the stars. But another way to look at that, notice it has the word real in it. So when you see sidereal, think real, thinks that's always going to be the best measurement. And we're going to do that by looking at the stars that are so far away, they never seem to move. We call them background stars. They're so far away, they're going to be the best thing we have to measure speeds. That sidereal day is going to differ from the solar day because how the Earth orbits as it's rotating. So if you kind of look here, notice here's planet Earth. We're looking at the sun and we're looking at a very, very distant star. Now, as we rotate around, we're also revolving, right? So we start here and we actually kind of go like this, and then we end up right back here. Now, right here, we seem to be pointing to a distant star right here, but remember, it's way off the page, way off the video where we can't even see it. So that star is located here. Kind of like how the North Star never seems to move. So we rotate it around, we see off in the distance that same star, but notice the sun and the star are now in different spots. And we still have to rotate just a little bit further in order to get the sun lined up again. So that's our 24 hours. So from here to here is 24 hours. From here to here is 23 hours, 56 minutes, and 4 seconds. This is definitely not to scale, but just to kind of try to show you the difference between the sidereal day and the solar day. And so if you turn on the constellations and hit go again, you'll notice how those constellations move throughout the year because of that sidereal day not lining up with the solar day, and that's why our constellations change, our view changes throughout the year. So obviously you're probably also familiar with these time zones, and if we have 360 degrees in a circle divided by our 24-hour long day, we have 15 degrees per every hour time zone. And then as you look out into the oceans, notice that's why we have roughly these nice similarly sized stripes. Obviously it's not perfect. That's because us humans, we're going to do whatever we feel like. Notice how part of Brazil and then Argentina, they kind of say we'll just all go together. If you notice, we're in Indiana. Notice how this means, yeah, we really should be in Central Time rather than Eastern Time. And here kind of shows you what that looks like. Blue would be the sun is going to rise early and set early. Red is going to be the sun is going to rise late and set late. And white is going to be, if you live there, your local time should be pretty lined up with the time on the clock. And you can see we're definitely getting into pretty red territory. So the last major timepiece to talk about is the year. And we have that basic idea of what a year means. It's the trip that the Earth takes around the sun. Remember, we always have the North Star in that particular direction. But just like a day, there's going to be a couple different ways we can measure a year. A tropical year versus, again, that sidereal year. So the sidereal year is going to be best. It's going to be the movement through the background stars. But what's frankly easier is the tropical year. And this is the sun cycling through the seasons. So remember, we can start the year at the spring equinox. The sun's on the equator, 0 hours right ascension. We get to summertime. The sun is now 23.5 degrees above the equator. And so that's the northern tropic line, the Tropic of Cancer. Then we go to the fall equinox. The sun drops back down to the equator. The winter solstice, the sun drops all the way back down to negative 23.5 degrees, 23.5 degrees south of the equator, or the Tropic of Capricorn. So that's what we mean by the tropical year, that motion through there. And in fact, again, they're different. 365.2422 days and 365.2564 days for the sidereal year, for a difference between the two of almost 20 and a half minutes, or 1,224.5 seconds. So this difference means a couple things. For starters, we're going to have to add in a leap year. So I got this little video to kind of show what's happening there. Notice the Earth is traveling around the sun in 365 days. It's fallen backwards. It's not exactly at the same point it was before by about a quarter of a day. So a year later, notice we're almost half a day behind. Another 365 days later, we're going to now be nearly 3/4 of a day behind. And so in 4 years, in 4 sets of 365 days, notice we'll now be nearly a day behind where we were. So let's add in an extra day. Oopsie, we're a little too far ahead now though, but we're almost there. So if we didn't add in leap years, notice what would happen. We keep falling behind more and more and more. Notice the years going up. Notice where January, December is headed to. It's literally falling backwards towards fall. So instead of being winter time, give it 400 years, we're literally going to have the calendar drift by an entire year. So if you think about it, if you're studying any history, and if we didn't add in that leap year, you might be reading about people fighting some battle in the middle of January, and you're like, oh, that's really cold. But if we didn't have this leap year, you would actually have no idea. Maybe January was summertime without that leap year. So with that extra little bit, we actually skip a leap year every 100 years, but keep them in every 400 years. So when you guys are old and gray and you make it to the year 2100 or whatever you guys want to call it then, I'll be gone by then. You will not have a leap year that year. But me, I graduated high school in the year 2000. That was a special year. We kept the leap year that year. So a leap year, we're going to add in an extra day every 4 years to keep the seasons. So we have one more type of year that we can talk about, the Julian year, which astronomers use and set it to exactly 365.25 days with 24 hours per day, just to make the math easier. So things aren't going to line up, but it's going to get it as close as we can, and we can at least do some math that makes our lives not so crazy as worried about all these just weird fractions of a year. So here you can kind of see what's happening, starting back in time, going forward in time. So we slowly drift off, add in a leap year, slowly drift off, add in a leap year, slowly drift off, add in a leap year. And you can see, so each spike downward, we're adding in a leap year. And so we spiked downward, but then the year 1800 comes along and we said, you know what, we're not going to add in a leap year. Add in a leap year again. And so then the next 100 years, we don't add in the leap year again, and notice where we get. And then we keep drifting downwards. Remember I said the year 2000, we did add a leap year back. And so we keep drifting down, no leap year. No leap year. And so you can see without that, we would just keep going down this way, and that's how the seasons would get off. But this weird little system keeps us roughly the seasons aligned. But notice this is also why, so this is the summer solstice, June 21st, June 22nd. That's why the day of the solstice and equinox can change over time because of this slow drift. But also a very big implication of this that was actually realized thousands of years ago. So we have this 20.5-minute difference between years. Well, this also means that the difference between the sun at those two times, between one tropical year and one sidereal year, is 50.3 arc seconds per year that the sun kind of falls behind there. So if we turn that into degrees, let's divide that by 3,600 seconds. We see that means that the sun is basically off between those two measurements by 0.01397 degrees every year. So if you think about this, remember we have 360 degrees in a whole circle. So how many of these little adjustments would we need to take a whole circle? So if we take 360 degrees divided by 0.01397 degrees per year, that means this cycles through every 25,770 years. Our planet is actually spinning like a little top. And this is called the precession of the equinoxes, this drift of the seasons over a nearly 26,000 year cycle. And really importantly, remember, we use that little that axis of rotation to talk about where the North Star is. This means Polaris won't always be the North Star. We're actually really lucky that it's so close right now. Thousands of years ago, it wasn't as close. Thousands of years from now, it won't be. You can go into Stellarium, go to today, you'll see Polaris sitting pretty much smack dab right at the celestial North Pole. And if you kind of go crazy adjusting the years, notice I went all the way out to the year 4000. Here's Polaris now. 6022. Look how far Polaris is from, here's the celestial North Pole, there's Polaris, our North Star. It's really definitely not the North Star. Notice right here, Vega. This is the brightest star in Lyra, really, really bright star. And actually, about 13,000 years from now, this will actually be really, really close and will become the best North Star. I tried to make Stellarium go out that far. I made it go, I think I almost got to the year 8,000. At that point, it shot me back to like 1850. I don't know what it was, but it took me a while to get there. So I can't show you all the way out there, but you can definitely see if you go really far out into the future, thousands of years out, you can see just how much the axis of rotation will precess, spinning like a wobbling top. So those are the major distinctions of time that we use in astronomy. It actually can get far more complicated than that, but hopefully this helps kind of give us an idea of what truly a day and a year mean and the different ways we can measure them in astronomy.